Hey, this is Mr. Hendrickson, and this is your Angled Projectile Rocket Lab Part 2 Prelab. Make sure you follow along, pay close attention, so you can answer all the web-assigned questions associated with this prelab. So as you'll recall, yesterday we took our rockets and found out the initial velocity with which they are launched off our specific launchers. When you go out today, again, make sure you're using the same rocket, same base, and same pump, in addition to the same cap. Hopefully you wrote down in the previous day's lab your cap number, which in my case we're going to call Z3, and you also wrote down the initial velocity of your rocket, which I'm saying is 25 meters per second. One additional item you're going to get today is a wedge. That wedge will allow your rocket to fire at some angle. So here's a quick snapshot of a wedge. This particular wedge is 35 degrees and 55 degrees. What you'll notice about your wedge is that 35 degrees is the angle of the wedge itself, but 55 degrees is the angle that the rocket makes with the ground. When we go to do our calculations, you want to use the second angle. What you'll notice on that wedge is that there are two angles listed. One angle listed, the first, is the angle with which the wedge is actually making when you slide it into the launcher. The second angle is the angle with which the rocket is actually launched. Your theta for this lab is going to be the second angle. Please make sure you record that immediately into your lab. Once you have all of that recorded, you're ready to go outside. When you're out there, you're going to need to go ahead and perform a number of calculations to determine how far your rocket's going to go and how long it's in the air. The first step to doing all of this, as with any projectile problem, is to take your initial velocity and angle and break it into components. This is going to require you to do some trig. In the first column, you're going to take your known initial velocity of your rocket, and you're going to take your theta and you're going to do some trig. Please use both trig identities and solve for both initial vertical velocity and horizontal velocity. The second step of this lab is, once you've found those initial components, you're going to use them to find the time of total flight. If you'll remember, as we've done in the numerous projectile problems, there are some things we know about time of flight. Remember, our rocket's going to go up, 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 and down, 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 down. We know a couple things about that path. Number one, we know at the very top, the y velocity is 0 meters per second. We also know that the acceleration of gravity at any point along this path is negative 9.8 meters per second squared. Because of that knowledge, in addition to our initial velocity we found from our components, we should be able to go ahead and determine how long it's in the air. And if you'll recall, the formula we use to do that is your final velocity in the y direction depends on your initial velocity in the y direction plus your acceleration times time. You have everything you need to substitute into this formula and solve for time. Once you have your time in the air, that is simply the time to the top. Remember, once you have your time up, you need to add it to your time down to find your time total. Please be careful that you do not skip this step. Once you have your time total, then solve for range. And to solve for range, you need to understand, of course, that in the x direction, our velocity remains constant for the entire path of the rocket. That means that if our velocity is constant, it only depends on total displacement and time. Fortunately, we've already solved for our Vx because we did our trig in step 1 and found our Vx component. And we also know our total time in the air from step 2, where we added our time up to our time down to find time total. If you simply plug in your known x velocity and your known time, you should be able to calculate your range. Now, one step that's not mentioned in the lab, which you're going to need to make sure you absolutely do tomorrow, is take your range that you find and you're going to need to convert it into yards. We want to be able to use Dushan field as our measuring device rather than have to bring a tape out. So, one thing you want to add into your lab at your earliest convenience is the conversion. We know, whether you search on Google or any other device, that 1 meter is equivalent to 1.094 yards. Once you have your answer from this column, you're going to need to go ahead and use this conversion, this ratio, to go ahead and convert that value in meters to yards. Once you have that value in yards, You're going to line your rocket up at the goal line and have your teacher walk out from the goal line that number of yards. For example, if your answer you calculate for range is 45 yards, you'll want me to stand on the 45-yard line directly in front of your rocket. If all goes well, I'll have to be dodging that rocket or possibly getting hit. The final piece of this lab requires us to calculate the maximum height with which our rocket reaches. Remember, the maximum height is reached not at the beginning, not at the end, but halfway through the rocket's path. If you watch your rocket from the side, you'll notice it go up, 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 and down, 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 down. The question is, what is this displacement at the very peak? Well, again, what do we know about this displacement? Of course, we now know the time because this is the time up that we solved for earlier. We also know the acceleration due to gravity is negative 9.8 meters per second squared. We know the velocity at this point is 0 meters per second. And we also know that our vertical velocity in the y direction is our y component that we solved for very early on. If we have all of these pieces and we know we want to solve for dy, it should become pretty clear which formula we need to use. You may want to look back in your notes as well, but that formula is dy is VIYT plus 1/2 AT squared. You'll notice that in this particular problem, we have our initial velocity in the y direction. It's our component that we calculated for very early on in the lab. We have our time up, which we'll use twice. In this portion, just the t goes in, and here it's t squared. Of course, we're also going to plug in acceleration of gravity, which we know to be negative 9.8 meters per second squared. At this point, you simply plug these values in and solve for dy. Your answer should be in meters. The process for firing an angled rocket is almost identical to your vertical rocket firing, which you'll remember from yesterday. The only difference is with firing at an angle, you'll go ahead and place the wedge under your rocket, so now your rocket's going to be fired with that initial velocity you found earlier and at some angle. Make sure you put the cap tightly over the top, slide the rocket body and nose cone over, make sure that your bicycle pump is attached to the rocket, and then you're ready to go. The last thing you want to make sure you do is make sure nobody is downfield from you and the area is completely clear. Make sure also the person pumping the rocket is far enough away that they won't get hit. And that's about it. Have fun. Once your calculations are complete, you can collect all your materials, including your rocket body, rocket cone, launcher, pump, wedge, and any other materials you brought outside, and make sure they all make it back in and in good shape. Then take a second, go back through your lab, make sure your work is complete, including formulas, substitute in, solving, answers with units, everything you're always required to do in a physics class. If that looks good, then congratulations, you're done with the lab. As always, thanks for watching, good luck, and remember, read the lab.